All right, so this is lecture 34, and we were discussing mixture fraction, and in the last class we understood that if we can get mixture fraction as a function of the spatial coordinates and time, then we will be able to get everything, because we can get the species mass fractions and temperatures as a function of the mixture fraction. So that was the whole idea. And just in the context of this discussion, I would like to spend a few minutes on equivalence ratio also, because I realize that there can be a scope of some confusion there. So for the equivalence ratio, we wrote phi, and what was that? If you check your notes, S YF naught divided by YO naught. Okay, and we were discussing, I think towards the end of the last class, about the location of the flame, and I told you the location of the flame is given in terms of the mixture fraction. It's a ZST, and ZST is Z stoichiometric. So I said that the flame will be at the stoichiometric value of Z. And in the last class, we had actually derived expressions for fuel mass fraction, oxidizer mass fraction, and temperature as a function of Z for a case when the chemistry was irreversible and infinitely fast. So we got those expressions for fuel mass fractions and temperature in terms of Z. And I said that, all right, those expressions can be divided into expressions which are inside the flame and outside the flame. Okay. But if you write expressions which are for inside the flame and then which are also for outside the flame, another set of expressions, then you have to know where the flame is. All right. And that the flame is actually at Z equal to Z stoichiometric, and Z stoichiometric was given by 1 over 1 plus phi. Okay. So I'll spend just a few minutes on this phi. So equivalence ratio, it so happens it's easier to understand in the case of premixed flames. The equivalence ratio, we are discussing this now more in the context of diffusion flames. So let's consider a situation like this. So some kind of a combustor in which we have two streams going in, and there is of course a stream going out, one stream going out. So this stream, this one here, stream 1, which has got fuel, that's this one, and here we have stream 2, which is oxidizer. Now we can write this phi as S times YF1 divided by YO2. Again, we have to be very careful about the notations. What is 1 and what is 2? These are the stream numbers. Okay. So YF1 is the mass fraction of fuel in stream 1 when the stream is entering the combustor. Okay. And what is YO2? It's the mass fraction of the oxidizer when stream 2 is entering the combustion chamber. So these are not mass fractions at some arbitrary place. Okay. It's not at some general place. So 1 and 2 are the stream numbers. So this is phi. Now the thing is, let's also see whether this is similar to anything that we know so far. Okay. is it actually same as the equivalence ratio that we discussed at the beginning of the semester, isn't it? Do we know that? What is S? S is in the context of something like this. Okay. So, this will give you S. So, S is actually YO by YF stoichiometric, correct? So, this is an oxidizer to fuel ratio stoichiometric divided by oxidizer to fuel ratio actual. So, this is phi. Now, there is also another phi which can be defined, which is called a phi g. So, this is called a global equivalence ratio. And that global equivalence ratio is not the same as the equivalence ratio that we wrote few minutes back. So, that is S times m dot f 1 divided by m dot O 2. Again, 1 and 2 are not powers as such, 1 and 2 are the stream numbers. So, this is a stream number and this is also a stream number. So, you will notice that the global equivalence ratio is written in terms of the mass flow rates, whereas the other phi is written in terms of mass fractions. So, is there a connection between the two? This is S times m dot f 1 can be written as m dot 1 multiplied by y f 1. So, what is m dot 1? It is the mass flow rate coming through that stream 1. Where is stream 1? Stream 1 is here. So, this has a mass flow rate of m dot 1. That multiplied by y f 1 will give you m dot f 1. All right. So, mass flow rate coming through this inlet multiplied by the mass fraction of fuel in that stream will give you the mass flow rate of the fuel coming through inlet 1, correct? Yeah.
So, in that stream, is there anything else other than the fuel?
In general, yes. So, we have YF1. So, YF1 is the mass fraction of the fuel. So, multiplied by so m dot 1 multiplied by YF1 will give you the mass flow rate of the fuel, and below we have m dot 2 not squared, m dot 2 multiplied by YO 2. So, same logic, this will give you the mass flow rate of the oxidizer. Now, you can notice that this is the other phi. the phi which I wrote few minutes back. This is the phi that I had written few minutes back. Okay. So, this is actually contained here. So, that means this is equal to phi into m dot 1 divided by m dot 2. So, this is our phi g, this is phi g. So, phi g, the basic expression for phi g, the global equivalence ratio is this one, but phi g is connected to phi through this expression. And what this also tells us is, if you have premixed combustion, then it is like only one stream. Okay. So, in that case m dot 1 is equal to m dot 2 equal to some m dot, and in that case the premixed combustion, right. If it is premixed combustion, we are talking about just one stream where fuel and oxidizer are mixed. So, then we have, there is no point writing separately m dot 1 and m dot 2. So, both of them are equal, the same thing. So, in that case phi g will be equal to phi. So, in case of premixed flame there is actually no difference, but in case of diffusion flames, in case of non-premixed system, these quantities may differ significantly. All right, now we will come to this question actually of where the flame is in terms of phi. The flame is actually at z equal to zst. Correct? And zst is equal to 1 over 1 plus phi, which is 1 plus s yf naught divided by yo naught. Yf naught and yo naught are the values of fuel mass fraction and oxidizer mass fraction in the respective streams. So, that means, remember that we have a fuel stream and we have an oxidizer stream. In the fuel stream, the fuel mass fraction is yf naught. In the oxidizer stream, the oxidizer mass fraction is yo naught. Okay. Where did we first get this? This sort of thing was first encountered when we were writing small z from capital Z, small z from capital Z. Okay. Small z from capital Z was this sort of thing. We wrote small zj as zj minus we did this, if you remember. Okay. So, we were using these values in the streams. That is how we got the zeros here, and finally after some work we saw that this z at stoichiometry is actually related to s yf naught by yo naught, and this thing is nothing but phi. Okay. So, the flame is at this position, which is given by this. But then there is a problem in the sense that I think one of you asked this towards the end of the last class, and I could not take it up in the last class. So, I asked where is the flame in terms of phi, and one of you said that this should be at phi equal to 1, isn't it? You said that this should be at phi equal to 1. So, is it at phi equal to 1? And I think I understand why you asked that question, because I actually had told you that some time back. In fact, I had shown you this flame from Turns's book. Okay. And I told you that this is at phi equal to 1. Actually, there is a little bit of problem with the notation. So, what we have is what, so this is turns. What he meant is phi is equal to s times m dot f by m dot o this is phi, following the usual definition that we did at the beginning of the semester. So, it is fuel oxidizer ratio actual divided by fuel oxidizer ratio stoichiometric, okay. And that is written as S multiplied by YF by YO. So, Y has S, where has S come from? S has come from here, okay. So, this is the usual phi. At the beginning of the semester, what did we write? We wrote in terms of air fuel ratio, I think, right? Did we write in terms of air fuel ratio? So, what was that? No, which one was stoichiometric, which one was actual? Okay, stoichiometric, and this is actual, correct?
The second phi is different, isn't it? Is it the global phi or it's the same?
Yeah, I'll just come to that. So let's just look at this first. I'll just come to that. In fact, look at this one first. Okay, so this is what we are most familiar with. This is what we did at the beginning of the semester. So is this correct? I mean, does this give you phi greater than 1 for rich mixture? Okay. Now let us see whether this and this are the same. So two things have been done. This was oxidizer to fuel stoichiometric on the top. Now it is fuel to oxidizer actual on the top. So that is correct. So it has been flipped in the sense that instead of air fuel, instead of oxidizer fuel, we are now writing fuel oxidizer. Fuel is to oxidizer. And since we are doing that, we have actual on the top and stoichiometric at the bottom. Is that all right? And can we write this equal to S times YF by YO? Okay. So S was what? S was YO by YF stoichiometric, isn't it? So the denominator here, this denominator is actually 1 over S. One over S. So this is correct. Now this can be, actually this can be if you multiply by some m dot flow rate, then this can be S times m dot F divided by m dot O. I mean this relation if you multiply it by m dot locally, there is some local m dot, let us say. So this gives you S times m dot F by m dot O from here to here. Now what turns meant is that if this is your phi, then that phi will be equal to 1 at the flame. So m dot F by m dot O has to be 1 over S at the flame. Okay. To illustrate this, suppose you have hydrogen plus half O2 giving you products. So, what is S? S is 16 by 2. Okay. 16 comes from here, 2 comes from here. So, S is equal to 8. So, if m dot H2 by m dot O is equal to 1 over 8, then that gives you phi equal to 1. Okay. So, that is how turns are defined it. Now, you see what is happening. This quantity now becomes 8 into 1 over 8 for this specific example. 8 into 1 over 8, so it gives you 1. So, according to this definition of phi, which turns is used, phi equal to 1 is a surface where m dot hydrogen and m dot oxygen are in the stoichiometric ratio 1 over 8. So, according to this, what do you think will happen if we go outside the flame? If we go outside the flame, what will happen to the value of phi? Phi will reduce. Okay. So, it will be phi less than 1. This is what that particular diagram had actually shown. Why is phi less than 1? Because if you go outside the flame, then your m dot H2 will come down and m dot O will be higher. So, in this expression, this part will become smaller. S cannot change. S is a given number. S is a given number, right? S is equal to 8 for this H2 plus half O2 reaction. S is 8 and outside the flame will have less value of m dot hydrogen. So, you will have phi less than 1. And if you go inside the flame, of course, you will get phi greater than 1 for a similar kind of argument. Correct? So, according to his definition, phi is equal to 1, but after that we of course made a switch. That is why I said we have to be careful about the notations. We said that now we are not talking in terms of phi, we are saying at Z stoichiometric we have the flame. But what is our phi? Our is important, not the phi that turns are used. What is our phi at the flame? Is it 1? No, because our phi is S times YF naught by YO naught, and this does not change spatially. This is a fixed number. So, this is a fixed number. Again, this will be clear that the phi is a fixed number. This will be clear if we take the hydrogen or oxygen example again, hydrogen oxygen example. So, we can have these things here. So, YF naught, let us say YF naught is equal to 1. What is YF naught again? It is the value of fuel mass fraction in that fuel stream, and let us say YO naught is also equal to 1. What is nu F? Nu F will be is a coefficient for hydrogen. So, our reaction is of course H2 plus half O2 giving you H2O. So, what is nu F? Nu F is 1. And what about nu O? From here half, so this is 0.5. S we already calculated, S is 8 and phi is S times y f naught by y o naught. So, this phi this is our phi. So, this our phi is actually 8. Okay. And what is Z stoichiometric? You have to calculate that. So, Z stoichiometric is 1 over 1 plus 8. So, 1 over 9 which is 0.111. And if you have CH4 air, for example, CH4 oxygen, let us say, instead of H2O2, let us make it CH4O2. So, for CH4O2, this is 1, 1, 1, 2 here, 2 for oxygen, this is 4, and phi will also be 4, and Z stoichiometric will be 0.2. So, 1 over 1 plus 4 which is 1 over 5. So, that is equal to 0.2. All right. So, what is the summary? Summary is that if we use that kind of definition which Stearns had used, this phi, then we have the flame at phi equal to 1. Okay. But we made a switch. So, our according to our notation, our phi is actually this, and this is a static number. This does not change over the domain, because this is based on S, which is a fixed number, and it is also based on y f naught and y o naught, which are defined by the streams. Okay. They depend on the streams. So, the value of y f naught here, the value of y o naught here, that define their values in the streams. In the domain, what happens, that we do not know. There will be variations. Okay. So, in the domain, this phi will not change values. So, here Z will change values, Z will vary in the domain, Z is mixture fraction, Z will vary in the domain, but the good thing is that we can calculate the value of Z stoichiometric and know the value at which the flame is. So, according to our changed notations now, so we are using different from terms. We are not talking about phi as giving the location of the flame. So, we are talking about Z stoichiometric giving the location of the flame. So, so these are these values. Okay. Now,
Basically, difference is previously like that phi equals 1, that is basically phi g equals to 1.
that is similar to phi g, yeah, because in terms of notations, it is in terms of mass flow rates. Okay. So, let us see where the phi g expression is. So, this is phi g. Okay. So, this is also S into m dot f 1 into m dot o 2. So, this is in terms of mass flow rates. So, this phi g is similar to the phi used by Stearns, but then the problem is these are still the stream values. They are still the stream values, whereas Stearns is using it as local values. Okay. Anyway, I think this probably would have been was a little unnecessary, but we had to spend this time to match the what we had seen in that figure from turns and what we are doing now. Okay. And let us think about the solution once more. Let us say we have a flame like this. One option would have been to solve for Vx, axial velocity, radial velocity, and Y fuel, Y oxidizer, and temperature using their basic equations. So, each one of them has a conservation equation, isn't it? So, there will be an axial momentum equation, there will be radial momentum equation, there will be fuel mass fraction equation, there will be oxidizer mass fraction conservation equation, there will be equation for conservation of energy which will have temperature. We will have various partial differential equations which are coupled to each other. So, solving that would have been much more difficult. Okay. Now, we are trying to solve YF and Y oxidizer along with temperature. We want to get all this, but to get all this we will have to try to get, basically first try to get Z, which is the mixture fraction. So, we now understand that that will be easier to first get Z, and then once we get Z, using those relationships which we got inside the flame, outside the flame, those are actually called state relationships. Okay, these relationships are valid inside the flame and outside the flame separately, different expressions, and these are the expressions which we did towards the end of the last class. Okay. So, we can use YF as a function of Z, YO as a function of Z, T as a function of Z inside the flame, then outside the flame, and get everything. So, that is the main advantage, that you have to solve for less things, and it is also true that this Z is in fact easier to solve. This Z is easier to solve because remember this is a passive scalar, this does not have a source term. So, this is easier to solve. So, I told you already about these issues, but there is just one more that I want to emphasize. The other advantage of Z is that if you wanted to solve YF and YO and temperature and all that in their basic form, then we could have done that. We could have said that okay, do not mind solving complicated equations for species mass fraction, conservation of YF, YO, and also energy equation, but that would have required setting some boundary conditions. Okay. Now, one assumption that we have made is that our flame is a thin flame, an infinitesimally thin flame, where irreversible infinitely fast chemical reaction is occurring. All right. So, by virtue of that, there is no fuel outside and there is no oxidizer inside. Okay. So, because of this, we could have applied for the we could have solved for the fuel equation only inside this, isn't it? We could have set YF equal to 0 at the flame. So, fuel conservation equation we could have solved, partial differential equation for fuel mass fraction conservation. We could have solved that in this domain, right, because outside that there is no fuel, correct. And similarly, for the oxidizer species mass fraction equation, we could have used the domain outside, because in any case there is no oxidizer inside. We could have done that, but even that would have had a difficulty. Okay. So, what I am saying is that fuel could have been solved only inside this, oxidizer could have been solved only outside this, but that would have had a difficulty. What is the problem? The problem is that if you want to take the fuel equation and set some boundary conditions, we will give some boundary condition on the axis, some boundary condition on this place, but we will need a boundary condition at the flame. Okay, at the flame fuel is 0. So, the boundary condition is at the flame YF is 0. Well, that is fine, isn't it? Because that is infinitely fast chemistry. So, we are solving fuel equation subject to this boundary condition as well as some boundary condition here, some boundary condition on the center line. That sounds fine, but there would have been a difficulty. The difficulty is that we would not have known where the flame is. To set a boundary condition somewhere in the spatial domain, you need to know where YF equal to 0. Where is YF equal to 0? Suppose I ask that question. I am trying to solve for fuel mass fraction equation. Where is YF equal to 0? If I tell you, YO is also 0. So, just focusing on the fuel mass fraction equation, I want to solve that. I set one boundary condition here, one boundary condition on the center line, okay, and we are trying to set some boundary condition on the flame. So, I say at the flame you set YF equal to 0. Fine, it sounds all right. But then where is the problem? The problem is we do not know spatially where the flame is. We do not know where spatially the flame is. But that is one of the reasons why we do not want to solve YF directly. Okay, because we do not have prior knowledge of where the flame is. But if we instead solve for Z, instead if we solve for Z, we do not need a boundary condition at the flame. Okay, we can solve for Z all over the domain. Using some boundary condition at the exit, using some boundary condition at the axis, using some boundary condition far away from the axis. Things like that. We could have done that, and the solution of Z in spatial coordinates would have told us where the flame is. Okay. So, setting boundary conditions for Z is not a problem, and then solving for Z is also not a problem. Once we get Z as a function of x and r for this kind of a geometry, we would have known where the flame is if we had done it that way. In fact, this is the way we should do. So, you have the Z values everywhere in the domain. Wherever I have marked, everywhere in the domain you have the values of Z. So, how do we now say where the flame is?
Solving for Z, we put Z equals to ZST.
Z equal to ZST. So, we have the numerical values of Z at various places in the domain, assuming we have done a numerical solution. So, you have done the values, we have got values of Z everywhere in the domain. So, you now see the locus of points where Z equal to ZST. That would be our flame. Okay. So, that's the procedure that we are talking about. From Z XR solution, we locate all points where Z equal to ZST. The flame is the locus of such points. So, mixture fraction has actually made our job much easier. But mind you, we are not actually solving this, and solving would take many more lectures. So, this is just the solution methodology that I have outlined. But people have solved this problem. People have solved this kind of problem for various kinds of diffusion flames using the mixture fraction approach. They have solved for laminar diffusion flames. They have also solved for turbulent diffusion flames. But let us take a simple situation when you have a tube, a circular port, circular tube. Through a circular tube, we are sending out some flow rate, which we call a Q dot F. So, this is Q dot F in general is the flow rate of fuel through the tube. It can have something mixed to the fuel. It can have something mixed to the fuel. So, it can have fuel plus nitrogen, let us say. And as we know, we will get some flame, and we can solve for this. We can get temperature as a function of spatial coordinates, species mass fractions as a function of spatial coordinates. We can get everything. And finally, as I told you, we can also locate the flame by using Z equal to ZST. So, we can get the flame length also. So, we can get the flame length. So, since people have already done the work, I will just write the expression that people have got. Actually, there is an expression which is a theoretically obtained flame length, which is this is log hard to read probably for you. Yeah. So, LF, this is theoretical, which is QF, that is the flow rate through the tube, multiplied by T infinity by Tf. Now, T infinity is the temperature of the ambient, Tf is the temperature of the fuel, and there is a D infinity. D infinity is the diffusion coefficient, is the mean diffusion coefficient evaluated for the oxidizer at the oxidizer stream temperature. And then this is log, this is ln. I think it is not very clear, but this is log of 1 plus 1 over S. S is a molar ratio of oxidizer to fuel, stoichiometric molar ratio of the ambient fluid to the nozzle fluid. So, I will just come to that. In fact, this is the general form of the solution that we have got for a situation like this, when there is flow coming out into the ambient oxidizer field through a circular port. This is for a circular port, not for a situation when you get a square port or a slot burner or something like that. So, this is a result, but you do not have to remember much of this, because we will use a simpler expression which people have obtained through experimentation, and that is of the same form. So, I will write that, and we are going to use it more frequently than the other one, than the theoretical one. So, this S is a molar stoichiometric, molar is important, stoichiometric oxidizer fuel ratio. This is this S. Okay, I understand that there can be again further confusion. This is not that small s which we are talking about. Okay. And this is again following Turn's notations. So, I am sorry it is getting a little complicated, but now we are not going back to the other theoretical analysis. So, we will just focus on this one. this S, this is a capital S which you see here, is not the same as that small s which we are using. So, this is a molar stoichiometric oxidizer fuel ratio, and for a hydrocarbon CXHY, for CXHY, this S is x plus y by 4 divided by chi O2. Okay. Chi O2 is a mole fraction of oxygen in the oxidizer. How do we get this? CXHY plus, if you write here O2 plus 3.76 into, okay. So, what do we write here? X plus y by 4, isn't it? That same thing has appeared here, and that gives you products, right. So, what is this chi O2? Chi O2 is the mole fraction of oxygen in the oxidizer, and it's actually 0.21, okay, usual case 0.21, and that will, what is 1 over 0.21? If you have a calculator, what is 1 over 0.21? I mean the exact value of 1 over 0.21. Anybody? Why I want this value is that, what's this? 4.76, right. So, actually that is why I waited, I wanted you to get this number. So, this number is familiar. So, what is that? That 4.76 is 1.3.76. So, this is 4.76 moles of air basically. So, this 1 over chi O2 makes sure that you get 4.76 if your chi O2 is 0.21, correct. If this is 0.21, then what is S? S is 4.76 into x plus y by 4. So, I am talking about the usual situation. Usual situation is air with 21% oxygen. So, in that case chi O2 is 0.21 and this S will turn out to be 4.76 times x plus y by 4. Okay. So, is that reasonable? What is S? S is supposed to be molar stoichiometric oxidizer to fuel ratio. So, is this molar stoichiometric oxidizer to fuel ratio? Should be, isn't it? Because for 1 mole of fuel, you have 4.76 into x plus y by 4 moles of air or oxidizer. Okay. So, this is what this S means. So, once you have that S, you can put that S here. QF is actually in your hands. The flow rate, it is a volume flow rate actually. Volume flow rate, otherwise we would have written m dot. So, this is this QF will give you the flow rate through the nozzle, and then T infinity is the ambient temperature, Tf is the fuel stream temperature. Fuel can be preheated sometimes. Okay, so this equation will help you calculate the flame length if the fuel is preheated also. So, you can have that value here. So, it is very easy. We do not have to use the theoretical expression, we can just use this to get flame length for various QF values, okay, for various QF values, and this is only for circular tube. So, whatever I have shown here is actually only for circular tube, and I just show you what happens as a consequence of this expression. So, let us say we have different fuels and we have the same value of QF. Okay. We have the same value of QF and we are determining using that expression that we saw 1330 etc. we are determining the flame length. So, the flame length is plotted as a function of S and for various fuels. If you change the fuel, the value of S will change, correct? The value of S will change if you change the fuel. So, what is plotted on the y axis is relative flame length, which is flame length divided by flame length for methane, right? And for methane, the relative flame length will obviously be equal to 1. So, that is on the y axis. What is the x axis value for methane? That is the value of S. What is the S value for methane? It is not the small s, we are talking about this capital S now. So, 4.76 times x plus y by 4, and what is x plus y by 4 for methane? 2. So, it is 9.52. So, that is what you see here close to 10, 9.5. Similarly, for ethane, propane, butane you can calculate the S that you require, and they will turn out to be points like this. So, it tells you that when normalized by methane flame length, it is actually this relative flame length is increasing as you go from methane with one carbon to ethane, propane, butane. So, 2, 3, 4 number of carbon atoms in the molecule. Okay. So, it tells you that if you go to these higher hydrocarbons, higher alkanes, they will require more amount of air. They will require more amount of air because S value will increase. What is S? For 1 mole of fuel, how many moles of air you need? So, that is increasing. As you go from methane to ethane, propane, butane, that is increasing, and as that increases, the flame length actually keeps on increasing, correct. So, this is from the expression that I just now wrote, but you can actually think about it more physically, more intuitively. This is expected, is not it? If a fuel requires more amount of air to complete combustion, what is S? S is the amount of air that you require to complete combustion of 1 mole of fuel, isn't it? Number of moles of air required to complete combustion of 1 mole of fuel. So, if you have a fuel which requires more number of moles of air, then the flame length will likely be more in that case, because you need a larger zone over which the combustion can take place to make sure that it gets adequate supply of air. All right. So, this is understandable, and the other observation you can see is that hydrogen or carbon monoxide, they have smaller flame lengths compared to methane. Why is that? Because for methane, for 1 mole of methane you need 2 moles of oxygen. For hydrogen and carbon monoxide you need half a mole of oxygen. So, the S value is even smaller. So, the S value is very small here. So, the length of the flame is smaller. So, at least so far we have learned that flame length increases linearly with the volume flow rate, that is QF, and flames for hydrocarbons which require more amount of air are in fact longer. So, these are good things to remember. Of course, we will analyze more results in the next class. So, we will stop here. Thank you.